Okay, the session is recording, and then let me start sharing. Come on. There we go. All right, and then that should come through in a moment. All right, so before I forget, ladies and gentlemen, let's start off with the code so that I don't forget. And the code will be 1 remember. I remember. Now remember. Spell that properly. Remember. Yeah, 1 remember. That is the code for today, so I don't forget. So there it is. So if you're watching this late, you can fill in the thing, but obviously don't skip the rest of the video. The codes are at random times in the videos, as long as we remember. All right, let's continue with where we left off. I will check the chat for questions periodically. So what we ended off with yesterday is we discussed the basics of what a class, some of the goals that we were trying to achieve, things like encapsulation, combining data and behavior into a single entity. And we were looking previously at can we achieve this using just C style structures and function pointers. We saw that it was a bit messy and didn't really work that well. So this week we've moved into proper C++ classes, and in the tutorials you can see we're building a UJ image, but this time out of C++ classes. So now we're just going to look at the theory notes related to that, but if you've been to one of the tutorials, then you will have seen this in action already, so it should be fairly straightforward. So let's continue. So working with classes and objects. Once a class is defined, variables of that class type are called objects or class instances, but mostly they're just called objects. And they contain the data and behavior within them. So like a structure, you can see that the variables, the member variables that are inside them, the data members as they're also called, are contained within that unit. They're encapsulated. And additionally, as you'll see, the member functions are grouped with them, creating this effect of encapsulation. So once the object is declared, then you can access the public members of the class. So unlike a C-style structure, there's different levels of visibility in a class and a C++ structure. Those levels of visibility are public, private, and protected. Public means it's visible to the outside world. From outside the members of that class, you can access that data or that behavior. Private means you can only access it internally within the class, and protected falls in between. We did discuss those ideas yesterday. So if you have a stack allocated instance of a class, so basically one that's been declared like a normal variable without the use of the new keyword, then you can access those public members by using the dot operator, also known as the member access operator. And you've seen that since last semester when you saw things like cin.fail or a string.length or all of those member functions that you accessed by way of the dot operator. And then you've seen it with structures as well. It's the same thing. The dot operator gains you access to those data members on the inside, or member functions in the case of a class. So that's that. Most of the things that you might want to do with a class don't work automatically as soon as a class is defined. In fact, the only operators, so an operator is basically the sort of punctuation like symbols that we use, things like pluses and minuses and multiplications and the arrow operator and dot operator and equals and equals equals and all of those various things don't work with the class the instant it's created. The only two that are even kind of defined are member access with the dots, and conversely also by extension the arrow operator, which as we saw was just a combination of dereference and dots, and assignment. The assignment operator that comes built in with a class doesn't work very well, and later on we'll discuss why it doesn't work very well and how we can fix it. But those are the only two things that really work: dot and by extension arrow, and assignment. Everything else you'll have to define by way of member functions, or as we'll learn later, through operator overloading. So it's our job to make our class as usable as possible by the people who we intend it to be used. All right, so here's just some examples. So here's assignment working. Assignment works fine if you've got nothing complicated going on inside your class in terms of its data members. If they're all regular variables or variables that have been created in such a way that you can assign them properly, things like strings and vectors will work fine. Normal primitive values like integers and doubles and booleans and characters will all work perfectly fine. Things that won't work fine will be fixed length and dynamic arrays, or anything that's been allocated with new internally. Those will suffer what we call a shallow copy, where only the pointer, for example, in a dynamic array will be copied, not the contents of the array, which can be very, very dangerous. And we will address that later. But if you've just got a boring which just has simple data members on the inside, or sophisticated data members that feel simple, like strings and vectors, then it'll work okay. So you can assign one object to another, and everything will be copied perfectly fine as long as those conditions are met. So we've seen that objects and also the data members inside objects have different lifetimes. So basically, if you create an object like a normal variable, like so, right? So let me just say if we had a notepad open, I had a class and I wanted to create an object of that class, and I did it like so, then this is going to be automatically managed. If we're inside a pair of braces, like inside an if statement or a function or whatever, then just like with an integer, the class will spring into existence over here and will cease to exist over there, and we don't have to worry about it. So most of the times, if you're declaring your objects as follows, like a normal variable, then you don't have to worry about the lifetime of the object. It will just behave like an integer or any other simple thing, and it will automatically go away when it goes out of scope, and that's fine. However, you can declare things as static, which means that their lifetime is going to be as long as the lifetime of the program. We will typically do that for data members, for constants inside the class, so that there's only ever one copy of the thing in memory, and it's available even if you haven't instantiated any object of that class type. So that's how we will mostly focus on the use of static. And then, as we saw, if it's a regular object declared like automatic, it'll have the same scope and lifetime rules as a normal variable. The data members that are internal to the class, so if we've declared them as follows, we have a class called C, for example, and inside it we have some data members, whatever. Then they will have basically behave like local variables inside all of the member functions for that class. So let's say we had a function, this is a private function, but whatever, so we can do this in a more organized way. But for inside this function f, we can access the variable I as though it were a local variable to f, and it's basically shared amongst all of the data member functions of class C. So and we can access it even though it's private, because if we're inside f, we are still part of the class. And then, as you saw, if you're outside the class and if the thing is publicly visible, you can reach it via the dot operator, via the member access operator, or the arrow operator, as long as it's publicly visible. Objects are what we call full class citizens of the language. So as soon as they've been defined, you can pass them as parameters, return them as return types from functions. You can pass them by value, in which case a copy gets made. That will have interesting implications in terms of the construction logic that they must follow, which we've covered in the tutorials, but They can be passed by value with copies being made, or by reference, meaning that changes to them are permanent and so on. In order to be passed by value, a full duplicate needs to be made. If the class just has simple primitive variables or sophisticated member variables like strings and vectors that handle their own duplication, then that's fine. You don't have to do any extra work. It will automatically be a proper copy. But like with assignments, if you've got things like arrays inside the class, or you've got objects that have been allocated with new and need to be deleted and so on, then you're going to have to provide extra logic to make sure that the copies are done properly, that it's an actual deep copy of the values and not a shallow copy of the pointers. So we will look at exactly how we achieve that. Now, we often have classes that are fairly big in memory, containers, for example. Let's say something like a vector. So if we have a vector of type int called v, contain a billion vectors, a billion integers, and somewhere along the line we have a function called f, which is going to do something with v, or do something with a vector such as v, p for parameter. What's going to happen here is a copy of p is going to be made, because this isn't being passed by reference. So there can be a lot of unnecessary work being done in memory. So what we often do is we mark this as a reference parameter, just so that it's much more efficient, that a full copy isn't made. And then because we don't want it to be changed, we actually label it as a const reference. However, the compiler has gotten very clever. I mean, it's been worked on continuously for decades now. So the compiler can often automatically detect whether or not it's safe to make a copy or do a sneaky move automatically when you call the function, depending on what you're doing with it. So sometimes it will automatically, even if you declared this as just a regular value parameter, it will detect that it's actually safe to do a reference pass automatically and not change anything and avoid the copy altogether. They call that copy elision. And likewise, if you never use p again in the code afterwards, it can even do what's known as a move using logic called move semantics, which will then, instead of copying the value, move the pointers, which is much more efficient. So it's still very common, and if you want to be absolutely sure about the movements that's going to occur with your objects, and you want to make sure it's efficient, it's still very common to pass objects by const reference, just to make sure that they're passed safely through constants and efficiently through references. But as I've said, these days the compiler is very clever and can actually skip all that work for you. So some people actually advocate just passing everything by value and letting the compiler sort it out, particularly with things like vectors. But just for what it's worth. So reference parameters are very common in object-oriented programming for that reason. You'll see them a lot. We'll use them a lot because of the amount of time it can take to copy the contents across. So this is what I've just shown you now, is that the problem is if you pass something by reference, it then becomes susceptible to accidental change, which you might not want. So you combine a reference with const to protect it and keep it efficient. When we're defining a class, we will typically define it in a header file, as you've seen in the tutorials. And for the member functions, we will typically just define a prototype for the function in the header file. We won't define the full implementation. Also, we'll declare the prototype. We won't define the full implementation there. So declaring is where you give the outline of what something looks like, and defining it is where you give the full implementation. So declaring a function is creating the prototype. Defining the function is giving the implementation. And in the case of classes, we will typically just put the prototypes in the header file and leave out any implementation. Some people don't program that way. Some people do include the full implementation in the header file, but we will avoid that because our goal, as you'll see, is to keep the logical properties of a class separate from their implementation details. It's a goal that we're trying to achieve called an abstract data type. And as soon as we start mixing in implementation details into the header file, we've now compromised that goal somewhat. So you'll typically just see the prototype of the member functions in the header file with the implementation in the CPP file. Then later on, when we implement it, we will fully qualify the name of that function by using the scope resolution operator over there. So later on, inside main, or inside the CPP file, we will have a function. C is the name of the class, F is the name of the function, and its return type was void, and then that's what we will implement in the main class. So this here is the scope resolution operator. You can also use it if you've got, for example, a constant, static, inside your class, and you don't want to actually create that class. So let's say inside main or something, you want to access that value. You don't have to do something silly like creating an object of type C and then going o.num, because why did I need to create that value? It's a constant that never changes. So what you can do instead is you could do C out and never instantiate the object, just use the class name C : num. That's using the scope resolution operator to access the static contents of that class. Both are acceptable. I'm now going to go check to see if there's any questions. Cool. Today's tutorial is available on YouTube. Yep, the link should already be up. In fact, it is. I put it there. When do we use the code I've just shared? Oh, yeah, so let's explain to you later, but that's just if you watch it late on YouTube. Does C++ automatically create a destruct? Okay, we haven't hit destructors yet, and the answer is a good question. I think it actually creates one that has a no op in it, no actual instruction. For the destructors, that's actually a good question. For the constructors, the rule is very clear, and we'll explain that in a moment. But for destructors, does it just leave it out, or does it create one with a no op inside? I'm not actually sure. It probably doesn't add an empty one unless you put one there. But I don't know that for a fact. It's a very good question. For the constructors, as I said, the rule is very clear, and we'll discuss it now. Destructors, interesting. So it's a good question. It's possible that it does. It's possible that it doesn't. I'm not actually sure. Yeah, it'll definitely have no effect. It'll be a no op if you haven't defined any logic for it. And it's hard to test because as soon as you put an output statement there, then obviously it exists. I think the only way to really know for sure would be to compile to assembly code and then look at the assembly code and see if you can see the destructor being defined there. So good question. Not actually as easy to answer as in the constructor's case. Yeah, so okay, this is a good point. So yeah, if we had that previous example with the value parameter vector, and you were then to pass it somewhere else, it would get copied again. And yeah, you could if there was some recursion going on, it could be a real nightmare. So definitely that could be very inefficient. And then let's take a look here. So if you've defined a variable within a class, will be known as an instance variable. Yes, from the point of view of the object. So let's just yeah, so if you've got an instance of the class inside it, there will be instance variables. We're going to use the term data members and member functions, which is the C++ specific terminology for the variables and functions inside a class. The more general terms, things like methods for the functions that are inside a class, is perfectly acceptable as well. For whatever bizarre reason, C++ has some specific terminology which means the same thing as general terms that are used in other languages. Instance variable is fine. We will refer to data members and member functions, in any case. And then yes, so a public instance variable would be a very bad idea, because what it would mean is it would mean something that can be changed. Let's say it's a normal variable. Let's say it's an array. It can be changed without following the rules of the class. So let's say someone just did this and our class is all working well and good, and they just said o.array and they set that equal to null, and that could lose us our array and cause a memory leak and break the class later on when it tries to access the array. So we will never have non-constants be visible publicly, right? They will be kept private, or later on, if they're to be shared amongst a family of classes, they'll be protected, but they'll never be publicly visible. Constants, on the other hand, no worries. You can make them as public as you want. No one can break them. No one can change them into a different value. All right, let's carry on. So you not necessarily. You need a destructor if you've got a resource. So a resource is something that needs to be managed. It's something you have to ask for, use, and release. So anything that follows the acquire, use, release pattern, you'll need a destructor to release that resource. And the only thing we've done so far that really follows that pattern is memory. So if you've got a dynamic array that you have to ask for with new and give back with delete, then you need to put the logic for releasing the array inside the destructor. If you don't have a dynamic array, if you've just got simple variables or things that manage themselves like vectors and strings, then you don't have to worry. It'll sort itself out. So you don't need a destructor unless there is a resource that needs to be managed by your class. Acquire, use, release. Yeah, so you'll see later on this semester we'll be introduced to another kind of resource, namely a file. Files are opened. You read and write to them, and then you close them, but you must never forget to close them. So it's good to put the logic for closing the file inside a destructor so it always gets closed. Likewise for, yeah, so that's it. Later in the second year, although you won't be using C++, there's other resources, things like network connections or database connections that must also be opened, used, and closed. So that's that. I am not sure what you mean by that. A general scope resolution, like namespace ... instead of using. I don't quite understand what you're saying there, so maybe ask in Discord, but I'm not fully sure what you mean by that. Yes, this is correct. The destructor will be called automatically when the class goes out of scope if there is a destructor that needs to exist. So in the case I had before where we had let's make it private, a private array of some sort. Okay, we'll need to define a destructor, which we haven't actually looked at yet, but let's take a look. It'll be called that. And we'd also need constructors and various other things, but let's just focus here. So in this case, the destructor for C would be called as soon as, let's say, O goes out of scope. Then the destructor gets automatically run. If there is no data that needs to be managed, then nothing needs to happen. Or if there is only simple data, let's say this was just a normal integer, we don't need a destructor, then that's not an issue. Sorry, I don't know why I made that destructor private. It should have been public. So that is correct. They do get called automatically when it goes out of scope. Or let's say we go back to having that, but let's just make it public. If we do something like this, let's say C pointer P is equal to new C, and then when we say delete OP, so when we delete the pointer to the object, then the destructor will run automatically. So if you've got a stack allocated object like so, then it will run as soon as this goes out of scope. If it's not stack allocated, if it's free store allocated, it will run when the delete gets triggered. So that's good questions, very good questions, thank you. Are we only working? No, we'll be working with abstract classes this semester, definitely, very soon, in fact. We'll start looking at the different ways we can realize abstraction, including abstract classes. And, well, they don't really exist in C++ directly, but interfaces in the form of abstract-based classes with pure virtual functions only. So, yes, we won't only be working with concrete classes this semester. All right, let's carry on. All right, so that's the scope resolution operator and so on. So here we're calling a member function set time to change the values of hour, minute, and second. Because those are private, we can't change them just by reaching inside using the dot operator. This is very common. In fact, there's a name for the kinds of functions we use to modify and retrieve values that are kept private. We call those, for modifying, we call them mutator functions. And for retrieving the values, we call them accessor functions. They're also very commonly called setters and getters for mutators and accessors, because they're almost always named set something or get something. So that's very common set of functions that you will include of member functions. So once the class is fully defined, you can use it in a program, and someone that's using your class is called a client of that class. So we must now shift our perspective. We're not just creating programs to achieve one particular goal. We're trying to create reusable data structures that other people might want to use. So for example, if you create a really good clock class, maybe any program that needs a clock will want to use it. Those are all clients of your class. So you're trying to make things as general as possible so that they can be as useful to as wide a variety of programmers as possible. So the goal is not to include problem-specific logic inside your classes that will make it unusable by other programmers. So here we see the term instance variable inside C++ specific parlance, data members and member functions. Once it's instantiated, though, instance variable is a perfectly good term, because every object, as you can see, will have its own copies of those variables. So the object is the instance of the class, the in-memory value that represents the class type, or a value of that class type. And you can see those values can differ, just like with a structure, exactly the same idea. And every object has its own instance of the data. The combination of the data members that have been defined and the actual values that are stored there is sometimes referred to as the state of the object. So in a sense, they describe objects as a mechanism for managing state, so that the state will only change according to the rules of your class. So for example, in this clock class, presumably you couldn't set an hour to be negative, or a second to be greater than 60, or something like that, or even greater than 59. So all that logic is set inside your class, which basically is a mechanism for managing that set of states. You see, very commonly you'll need to retrieve values. Functions that retrieve a value that's private internally is called an accessor function. Those that modify the value of a member variable are called a mutator function. And functions that don't have an effect on the state, that don't modify anything. So let's say we had f here, and all f does is print hello world. It doesn't actually touch int in any way, or even prints this variable out, but doesn't modify it. We can label those const functions. It's basically a signal to the compiler and to the users of that class that you can safely call f without modifying the values inside the class. It can read them, but it won't change them. So your accessors will always be, let's just call this A now. Let's call A. I will typically name my member private member variables with an underscore in front of them, but you don't have to, but it's one way to visually denote them. And let's say we had a get a member function, accessor function. We could call it get a. And then we could label it as a const function by putting the const keyword after the closing parenthesis for the parameters. And this basically indicates to the compiler and users of the class that we can call get a, and it will not change anything inside the class. Okay, abstraction versus encapsulation. Okay, that's a great question. So what is the difference? Encapsulation is basically bundling things together. It's taking data and operations that are legal on those data and storing them in a single unit. Abstraction is taking specific details out of a solution so that you have a solution that can apply to a wide variety of different contexts. There's a lot of different ways of doing it. One of the ways of doing it, which we'll see, is you've already seen things like vectors. A vector is a container, but a container of what? It's a container of anything. So the notion of what's being contained has been abstracted away using a mechanism known as generics. So a vector of int, or a vector of char, or a vector of bool, it doesn't matter. That's one way to achieve abstraction. Another way is to have a family of related classes that basically allow you to make very specific versions of a class and have more general or abstract versions of a class to use later. So for example, you could have a class that represents a person and a class that represents a student. A student is a person, so any function that can work on a person can also work on a student. That is one kind of abstraction where the person class is more abstract than the student class, which is a specific kind of person. We'll discuss that in the coming weeks. So that's another way that you can achieve abstraction. But abstraction is actually achievable by a variety of different techniques. And it's anywhere where you basically make your solution general enough so that it can be reused in other contexts. Yeah, so that's that. Let's keep going. So yeah, so unwanted details, or let's say problem-specific details, and then basically focusing only on what he's calling the essential info, which that makes perfect sense. So basically, you separate the problem-specific details from the what we call problem invariant details, so that the invariant stuff can be reused without worrying about the problem-specific details. And as I said, there's a variety of different techniques that we can use to achieve that. Yes, so that's a perfectly good example, combining both abstraction and encapsulation. So the combining is the encapsulation. How does the calculator store its values? It stores them inside some sort of register, some sort of state representation. How does it actually implement multiplication? What's the exact logical circuit that gets used to do it? We don't know. We don't care. We just know that we can say what 5 plus 1 and get 6. So that is a very good example. All right, so we've mentioned the use of the const keyword. Let me just see what. Okay, so yeah, let's keep going. We've mentioned the const keyword as it applies to member functions. So C++ doesn't have a fixed order in which we declare public and private members. And for what it's worth, the default for classes is private. What we're going to do is our standard, but I won't penalize you if you do something different as long as you're consistent. But the way we're going to do it is we're going to start with public and then switch over to private later. And the reason for that is that people read from top to bottom, and the client programmer who's reading the header file for your class is interested in the publicly visible functions. They don't care about the private member functions and data members, because that's problem specific, or that's something that maybe you'll change later. They don't care. As long as the public interface stays the same, they're happy. So we're going to put it in order that the person who's reading your class would find it useful. That means public at top. But other people do it differently. So as long as you're consistent, just don't be weird and like alternate and have some public and then some private and then some public again and then some protected and then some private and some public. That's just chaos. So that's as long as you're consistent, we'll be okay. All right, so the constructor's purpose is to initialize and allocate resources. You can have many constructors because there's many different ways you might theoretically want to use an object or create an object. So we will create ones with parameters. We'll create ones without parameters, which are often referred to as default constructors, but I have a slight objection to that, but it's very common, so I will explain my objection in a moment. And the name of the constructor is the same as the name of the class itself, but with no return type. So for example, a constructor for C over here would literally just be called C, and we could have another one that instead takes a parameter for A, and so on. So you can have as many constructors as you want as long as their parameter lists differ, because they're just functions at the end of the day that are being overloaded. You don't call them manually, right? They get called automatically under certain contexts, like when you instantiate a variable of that type, or if you pass it by value, a particular kind of constructor will be called, or if you create an array, a fixed length array of that class type, then a constructor will be called and allocate them. So the exact constructor that gets called, it depends on how you actually created the object. If you passed parameters, then the ones that match those parameters will be called. If you didn't, then the parameterless no args constructors, also known by some as the default constructors, will be called. So the constructor is automatically executed when the class is instantiated into an object. And because a class may have more than one, you can invoke a specific one by passing the parameters to it. So creating just a normal stack allocated instance of your class, we'll call the, in this case, the constructor with no arguments, the no-args constructor. Or if we specify one with the parameter list, like you saw a moment ago, when we call it, if we pass parameters to it, then that one gets called. Now there are, as we mentioned earlier, very specific rules about when classes get constructors. So if you provide a constructor, obviously the class will have constructors. You can have classes that have constructors that have default parameters, just like normal functions can have default values. Their parameters can have default values. And you can have a constructor that has no parameters at all or only default parameters, which gets called automatically. And we call that the default constructor. But there's a related concept that is worth unpacking. All classes have at least one constructor. If I created another class over here, B, there's literally nothing in it. It has a constructor. C++ will automatically create a constructor called B, which takes no parameters and does absolutely nothing. So it gets that constructor by default, right? However, if I created another constructor, say one that takes a parameter, now C++ will not automatically add a no-args constructor to this class. It only has one constructor, B. In this case, it has one constructor, B, with no parameters. So that's an important thing to note. So it's very common and a good practice, even if you don't think you'll really need it, to automatically add a no-args constructor yourself. Because no-args constructors get called, for example, if we created an array of type B that was fixed, we call this constructor on every single element of the array. If we did this, it doesn't have a no-args constructor. It's now impossible to create fixed-length arrays of that class type. So just for what it's worth. So the nomenclature that I will use is I will refer to the free constructor that gets automatically added to a class as the default constructor. And constructors that just happen to have no arguments, I will refer to as no-args constructors. That's not a fully standardized. You'll have some people who consistently use the nomenclature slightly differently. I've picked a nomenclature which is more similar to the one that you would find in Java, so that there's less of a transition bump. But yeah, so the textbook, and you'll see others will refer to even an explicitly defined constructor with no arguments as the default constructor. I will specifically refer only to the free one you get when you don't provide any other constructors as the default constructor. Let's just see if there's any other comments, questions. Okay, can I have two default constructors? No, that would be ambiguous, and it's a great question. So if there's any ambiguity in the constructors, it will fail when you try and instantiate the object, because it won't know which one to create. And if you've got two defaults, that will cause that problem. You can have a number of constructors, but they must be distinguishable by their parameter lists in particular. You could even have ones that, let's say, like this, if we had a default value for B, which could be confusing. For example, if we just created a B of type B, which one is supposed to be called here? The no-args constructor or the one with the default constructor defaulting to 0? Maybe they behave very differently. So that will cause a compilation error because it won't be able to disambiguate between the two possibilities. It's an issue. It's a very much a personal view thing there. So is it more semantic than syntactic? Yes. It doesn't have any influence on what you would write as code. It's just the word I'm going to use to refer to things. I'm going to refer to the free constructor you get if you've got no other constructors as the default constructor, and a constructor that has no arguments as a no-args constructor. But that's just to bear that in mind. Do they go together? There'll be different ways of creating the same object. Yeah, so it basically gives you choices about how you're going to create it. What that means depends on your problem domain. Do we only include constructors in public? That is an excellent question, and the answer is 99.999% of the time, yes, your constructors will be public. Sometimes, however, you'll want to prevent someone from doing something. Like, let's say, for example, we had a class that just represented like useful constants. It was filled with static constants that we thought were just absolutely phenomenally useful. So 0 and 1 and just amazingly useful constants, just the best. And we were using this basically as just a container for these related constants. And we expect people to use it like this, useful constants, : 0. We don't actually want them to instantiate the object. So let's stop them from instantiating the object, because someone could be weird and go like, as I said, useful constants, UC, and then go UC.0, which is fine, but it's dumb. You could, if you wanted to, block someone from instantiating the class by having a private, sorry, not public, a private constructor. And it's now impossible to instantiate this class. You can only use its static member functions if it had any data members. So that is, well, actually, yeah, class constants in this case. So that's one weird example where you might not, but almost always you will have your constructors be public, because the whole point is they should be externally visible so someone can instantiate your class. A very good question. All right, so here's just examples. Yeah, creating an array, a fixed length array of your thing. That's called the default constructor on all of them. Destructors, as we saw, those are things that don't have that will deallocate. They look like that. And let's go back to imagining that this was an array. Your destructor implemented as follows, and it would do something like, let's assume that that was an array. It would then handle the job of releasing the, in this case, deleting. So a destructor, there'll only be one destructor at most. So there can be 0 or there can be 1. 0 if you don't need to free anything, and 1 if you have some logic that needs to run when the thing gets destroyed. Whereas you can have, and will probably have, many constructors. Okay, so I think we're, yeah, this is where we're going to stop. So we'll pick up on Friday with Mr. Satungu. I think we are out of time now. Yeah, 17:05. So if there are any final questions, please ask them in the chat. Okay, the scope resolution operator is used to access members of a class outside the class. So this is a great question. Let's take a moment. The attendance code was given right at the beginning of the class. So when you watch, you don't have to worry about it because you're here, but literally I did it first thing. Okay, but so that was a very good question. Difference between blah and blah. Okay, so if I've got a static constant like we had earlier, class C and we had static int I equals 1 const. Then when we access it, we'll go scope resolution operator like so. If we have a normal member function that we're going to access after instantiating, so let's say, for example, let's make it a function because we don't want to give examples of publicly visible variables. Then we would do, we'd create an instance of the class, and we would go c.f. Right? So if it's being accessed through a stack allocated variable dot, if it is static, let's say we were outputting it or something. If it's static, then we will use the scope resolution operator like so. And if it's normal access through a normal variable, it will be a dot. And then just for some completeness sake, if we've got it through a pointer, then it will be an arrow. So those are the three. Obviously, then it would be our job to delete OP at the end of the day. So those are the three ways that you'd access it. Scope resolution for static stuff, dot for normal stack allocated stuff, arrow for heap allocated stuff. And the only other place you'll see the scope resolution operator is when we implement these functions. We will implement them with the name class in front, and then the function name there, and then implementation details over there. So that was an excellent question. I hope that clarified it. What happens if we have an external pointer not belonging to an instance of any class, pointing to a portion of the memory that's defined during the lifetime of the object? Then we destroy it. So that is an excellent, dangerous thing that can happen, is we must never have functions that return pointers. Let's say there was an internal array, blah, blah, private here. And inside F, we did something terrible like return underscore A. Then someone could do something terrible like deleting this array without our knowledge. So that is a very, very good point. That would be a violation of the encapsulation. So that is excellent, excellent question. Why did I put the tilde behind the C? That's to differentiate between the constructors. Let's put them back here. So let's say a constructor will just be a C, and then have different parameters, and the one and only destructor will have a tilde in front of it. So this tilde says this is the destructor. Its job is to destroy the thing. This is the constructor. Its job is to make the thing. So that's a very good question. All right. So I said, what contributes to one being a good programmer, being more theoretical or practical? So for 1B, your second semester test is still practical. So you have to focus on it like you would in 1A with lots of practice. The exam is theoretical, but because they're being asked remotely, it'll be quite applied. It's a difficult question because they're both important. I'd say when it comes to theory, the most useful thing you can do is pay attention to the maths side of things. So pay attention to your vector algebra and your graph theory in mathematics. That will help you be a better programmer from a computer science point of view. So focus, you can pay attention very closely to your programming in computer science class, but to be a good computer scientist, you also need the math side of things, in particular vector algebra, matrices, and graphs. That's my advice. There are different paths though, but that's a great question. All right, so thank you very much. I think we're done. I'm going to stop recording now. And I hope you guys have a great evening. And then as soon as this is indexed, I'll post it on the website. And then Mr. Satungu will finish off. Okay, thank you very much.